Let's finish up by looking at a few mass spec methods, both ionization and detection, that is used besides gas chromatography mass spectrometry. LCMS and MALDI-TOF, really important in biochemistry, in protein, proteomics, stuff like that. So we're going to just briefly touch on these other uses of mass spectrometry. Again, every mass spec has a ionization method and a detection method. And so far we've really focused on electron impact as our ionization method. There are other gas phase methods. Chemical ionization is one of those, where you have some kind of gentler way to get a charge on a compound. We're not going to talk about that here. What I want to focus on is liquid phase stuff. So what about molecules that I can't get into the gas phase, right? So, we were lucky to get eugenol in the gas phase. We needed to do steam distillation to make that happen. What about big molecules like proteins that I'm never ever going to get to actually boil, right? Then I have to be clever. So one thing I can use is electrospray ionization. This is often linked with HPLC, so it's HPLC-MS. If you remember when we talked about chromatography, HPLC is kind of like your TLC plate, but reverse phase. So it's a nonpolar column. Water, methanol is your solvent. It's really good for separating polar stuff that can't vaporize. So this is great for, again, especially small proteins. Okay, this is an electrospray setup. So the idea is that I've got my HPLC on the left side of this, and it is separating stuff. And then once I separate it, it's going to come in the left side here. Okay, so now I've got sort of things coming through this spray needle capillary. So there is a giant voltage drop coming in here. So when I look at these little droplets, they're carrying quite a bit of charge. And so here's a zoom in. So I've got these this big voltage drop here creates these droplets with a lot of charge that, because the charge repels itself, it kind of surrounds on the outside of this big droplet. On the inside of the droplet, I've got solvent molecules, again, typically water or methanol, and I've got some of what I call the analyte, which is the stuff I actually care about. So I've also got hot gas, like hot air or hot nitrogen, kind of flowing past this needle. And so this hot air is evaporating a lot of these solvent molecules off, but I'm not losing charge. And eventually what happens is I have this tiny droplet now that has the same amount of charge as the big droplet did. And that charge kind of eventually gets to a point where it's too much charge for too little area, and the little droplet explodes. And it explodes to give me like one analyte, maybe a couple of molecules of solvent around it, but eventually just analyte, right? So here I've got just the molecule I care about with a charge glommed onto it. So maybe that is just an extra, maybe it's just an extra proton, maybe it's an extra sodium ion or a potassium ion, but now I'm not talking about ripping electrons away or ripping anything away. I'm glomming some charged species onto it, but the whole thing is now charged. And that charged thing will end up going through this capillary and then to my mass spectrometer. Okay, so again, there's no radical cations formed here, and all my ions are either M plus H, M plus Na, maybe ammonia, something like that. I'm not going to see a whole lot of fragmentation, but I am going to see multiply charged ions. So remember, for GCMS, we kind of said, well, it's technically a mass to charge ratio, but you only have one charge per ion all the time. That's not the case here. For lots of times, like if I have a protein protonated some number of times, I have to actually do math to calculate what my mass to charge ratio is. Right? It's going to end up being M plus N divided by N. So for instance, here is horse heart myoglobin. It's about 17,000 grams per mole, or Dalton. Dalton's another way to say grams per mole. And so here, this spectra might at first blush look like I've got lots of fragmentation, starting at the right and kind of fragmenting down. But that's not what this is. These are all the same molecule. They just have different protonation states. So for instance, this one has 10 protons attached to it, this one has 11 extra protons attached to it, and so forth. You can see the thing with 20 protons attached has about half of the mass to charge ratio as the thing with 10 protons attached. Right? But the really cool thing is if I zoomed in here and I looked at how close these are, in a normal GCMS I'm only going to see kind of like 1 Dalton differences. But here I'm going to see 0.1 Dalton differences because I'm dividing everything by 10. So that's a good sign of when I have polycharged compounds, polycharged ions. So I'm not going to see I'm not going to see much fragmentation in electrospray on its own, but I might want to induce fragmentation. So I want to break it up to get some of that chemical information, right, about what pieces it's likely to break up into. And for something like this, I might use just something called MSMS, or MS to the N. So the idea here is that I essentially have 2 detectors here. So my first detector only lets a certain mass ion through, but now it lets it through into this area, and now I'm going to bring in some carrier gas or collision gas like nitrogen or argon to break it up, right? To kind of like just knock it to pieces. And then once I have the pieces, now that goes to a second detector where I can select out. So it's kind of like using MS on a fragment. So sometimes this is called a triple quad, where I've got one quad in front selecting an ion to look at, another quad colliding with that ion, and then I can look at the products that come out of that. So LCMS is really, really important in protein structure determination. So here you have I think it's a 9 amino acid peptide, and this might be raw data, and a computer or you can go through and actually figure out sort of where the cuts are in this compound that give us the peaks that we see below. So the A and the B are kind of the language that mass spectrometers use, but you can see like this YSHF thing, that is tyrosine to phenylalanine, so kind of that piece like that. But we can, essentially once we get this to smaller peptides, a computer recognizes the patterns that smaller peptides give. And again, if we used MSMS, the slide I had before, I could ask it, hey, take that 535 peak and further fragment it to see what kind of pieces that's going to break up into, right? That's a great use of MSMS. So again, here's another example. So this is very, very widely used to figure out what kind of structures we have. Much better than some of the old-fashioned methods where we just have to kind of break it up piece by piece in the lab to do it. Okay, so all that is liquid phase solution stuff. What if I've got a compound that I really can't even get into the solution phase? That's not dissolvable. Well, I can do solid phase mass spec. Call it MALDI-TOF. So MALDI is the ionization method, matrix-assisted laser desorption ionization, and TOF is the detector method. So essentially, this has like a little joystick, and you load up a little bit of your sample in a little divot, and that sample has, again, some of your stuff of interest and some of a matrix, just kind of a crystalline compound that you sort of mix it with. And you put it in the machine and you aim a laser beam at it. And the ones that I've used actually have a little like Atari 2600 joystick with a button that you push on it. That laser beam is going to just almost physically knock some of these atoms or molecules in the air. Right? So it's going to knock some of the molecules of interest, it's going to knock some charged compounds, and eventually some of those will glom together and we'll get some charged species in the vapor phase just because they kind of got just knocked into the vapor phase. Once they're in the vapor phase, we're going to use time of flight to get a detector. Time of flight is pretty much the simplest detection method you can do. I'm just measuring how long I'm going to accelerate all of these ions with a known energy. And the bigger ions, that's not going to change their momentum that much. They'll be going slow. And the little ions, that's going to be like super hard push, and it's going to be like taking off. So when I do TOF, time of flight, I'm just looking for literally the time it takes them to fly from the ionizer to the detector, because smaller compounds will go faster and bigger compounds will go slower. You can even do this with microorganisms. So I can shine my little laser beam at E. coli, and I'll get a kind of fingerprint of the proteins that are expressed on the surface of the microorganism. Again, these are big numbers, 4,000 and 8,000, and that's just the mass per charge. So maybe I'm looking at a 80,000 Dalton protein with 10 charges. But this is kind of used sometimes, again, in proteomics to sort of map out, like, okay, these are the kind of proteins that I typically see on this microorganism. So again, this is more of just an informational video, I guess. But those of you that continue on to talk about biochemistry and maybe even do some research in that, you're going to be running into MALDI and lots of different electrospray methods. And remember that when it comes to mass spec, there's always the same two things that you need to do. You need to get a charge onto something, and then you need to manipulate that charged ion in order to detect it. And so, as long as you have those two things, you can look at pretty much any charged compound.